a little bit of a tutorial on how to actually perform major tasks in self-driving cars. For example, when it comes to the typical software stack that you see in a self-driving car, where you basically have that the sensors that provide you with sensor data, then you typically have that what is called an interpretation module, which I briefly cover only in this presentation. Then it comes to mapping and localization, and this is one of the key tasks, and actually also was one of the enablers of the self-driving car development, that we all of a sudden, like 25 years ago, realized how to basically do localization and mapping in an efficient way. And then it's prediction, planning, control, and that is then sent to the actuator. So we will mostly in this talk focus on those two components here, namely the mapping and the localization task, in order to actually tell you like what it means to build a reliable self-driving car, which basically has to fulfill three functions. First one is stay on the road, which is localization. The second one is don't get hit. And the third one is don't hit anything. When you can accomplish those, then you get really, really far. But in this talk, we're trying to focus on this perception task, which is state estimation or localization, and also a little bit of mapping. And we are going to do this using like uncertain explicit representations of uncertainty, which is basically that what is behind probabilistic robotics. The interesting aspect of probabilistic robotics is that you can actually derive everything from basic principles. And that's why I'm also like showing you here the actions of probability theory. These are the three over here that you actually need. Some students typically ask the question, why is this P of non-A equals 1 minus P of A not in here? You'll see this in a few seconds. So further look at action 3, which is also often a little bit confusing. Just to a refresher, start easy. That's what we're doing here, right? So the question is, why do we need to subtract this thing here at the very end, which is basically the intersection between the two disks. The reason for this is if we add those two disks, we count the intersection twice, and this is why we need to remove it once. For us to, like, in case you started doubting at this point in time, I hope that helps you. And then the other question that I mentioned, right? Why isn't P of non-A equals 1 minus P of A not in the axioms? Mathematicians are also always minimalists. They're actually trying to minimize the number of axioms that you need. And because you can derive this from the use of all three other axioms, you can basically directly remove it from the original set of axioms. Right? So this one can be derived from the three axioms that I showed. In this entire space of state estimation, you are basically confronted with two types of variables, right? One is the so-called discrete random variables, where every variable can only take a discrete number of values. But then on top of this, there might be continuous variables. So, and these continuous variables are basically continuous functions, and there you cannot give a probability for an individual value. Rather, you always reason about these intervals here. But in principle, everything is very, very similar here, right? Another fact that we will make use of is that in the discrete case, or in the general case, in discrete and continuous case, these probability densities typically sum or integrate up to 1. So the area under the curve is always 1. And this is something that we will need in a few seconds. Then joint and conditional probability is also something that is a concept that needs to be explained briefly. So first of all, we can have like these joint probabilities, like P of x equals x, small x, and y equals small y, which we typically denote as P of x and y in short. This is basically the probability of x and y happening at the very same time. And then there's this notion of independency, that when basically x and y are independent, then we can write this as P of x times P of y. Then there's another term that is like with this vertical bar, which is the conditional dependency, right? Which is basically P of x given y. And this is a definition that we are using here right now. Basically, what we're saying is P of x given y is P of x and y divided by P of y. And if you don't like this division, potential division by 0, then you can also define it like this. P of x and y is P of x given y times P of y. This is all that we need in order to introduce these conditional probabilities. And in fact, if x and y are independent, then y doesn't provide any information about x, then P of x given y equals P of x. There's a few further laws that you can derive from this. One is the so-called law of total probability. P of x is a sum over all y, P of x given y times P of y, which is frequently used when you have, like, for example, multidimensional tables to basically evaluate like the probability of x given joint probabilities. So this that you find in tables, and you can have the very same in the continuous case. But in principle, what we are doing here is you're basically like summing over all y, and then we sum up all the values for P of x given y times P of y. And this is directly equivalent, if you remember the definition, of P of x equals sum over all y, P of x and y. Same for the continuous case. This is called marginalization. We will need this in a few seconds as well. And the most important formula in this context, probably all of you know this, is Bayes' formula, which basically is P of x given y is P of y given x times P of x divided by P of y. Those three terms, you have individual names. This is the likelihood. The top one is a prior, and the bottom, the denominator, is the evidence. And this directly comes out of the definition of conditional probability, right? If we just like use the two variants that we can have for P of x and y over here, and then make a division by P of y, then we end up having Bayes' rule directly. And this is something that we are going to need through the derivation of that, what we call the recursive Bayes filter. And here's something that it's typically very hard to understand for students, and sorry for bringing this up, but we will definitely need this for implementing a self-driving car. So when you look at Bayes' formula, it basically says that P of x given y is P of y given x times P of x divided by P of y. Turns out that this term down here, P of y, does not contain x. So we are typically interested in the probability distribution over all potential states of a system. In localization, it's all potential positions of the vehicle, given all the data that we gathered. Right? And this P of y, the probability of all this data, is independent of where the vehicle actually is. We can see this, that x doesn't appear in here. So even if you like use the law of total probability and sum overall and calculate what P of y is, then you end up having this term, the sum over all x, P of y given x times P of x, which is, if you look at this equation over here, right, it's exactly the sum over all x. Or what we're basically doing is we're summing up all the nominators over all x. Right? So this is basically that what we are doing, and we're going to utilize this in a few seconds. Right? So this is what you actually need. So this basically means that P of y is a constant, right? Because it's a constant for all x, right? And this constant, it makes sure that the left-hand side term of this equation sums up to one over all x. This is why this is called normalization. And this is a constraint over this value, which later on will allow us to basically not exactly specify it, but we can basically derive it from the calculations that we are doing. And this is, and that makes it very, very handy. Another aspect is that you can always also introduce background knowledge, right? So you can add whatever evidence you have to every term, P of x given y plus a, and then you basically add this a to every term in the equation. You can do this wherever you are, whenever you have an equation, you can do exactly this. A few words about conditional independence. So we spoke about independence, which basically means P of x and y equals P of x times P of y. But there's also conditional independence, which is different, which basically means that P of x and y are independent given Z. In this case, we will see this in a few seconds. In this case, we basically specify, can write P that this is equivalent to P of X given Z and P of Y given Z. Which basically means X and Y are independent given Z, which is not necessarily the case without knowing Z. So there are situations where X and Y are not independent, but they become independent once we know Z. And this is something that we will also see in a few seconds. So this marginal independence does not mean independence. Now let's come to the Bayes filter framework. This is like a long equation that we are going to derive in a few seconds with everything that we have at hand thus far. So what we're typically given is a stream of data. So imagine our system has controls and sensors. And so the controls are denoted as U's and the sensor measurements are denoted as Z's, perceptions. The controls are typically used to change the world or the state of the system, and the measurements are usually used to estimate the state of the system or even the world. And for this, we assume that we have two functions. The first one is the so-called sensor model, which tells us or gives us the likelihood of the observation Z given the state X. So we're asking basically the question, what is the probability of measuring 1.5 meters given the system is 1.4 meters away from the next obstacle? And then we also have a so-called action model, which provides us with the probability of ending up in X given we were in X prime before and executed an action U. Basically tells us, like, so-called also nowadays it's also called a world model. It tells us like how does the world change given it was in a state before and we executed a certain action. And then in the end we also need like the prior, like what is the initial distribution, but there we, as we will see later, we can basically also often assume that we have no information in which case this is just a uniform distribution. And what we are interested in now is like estimating the state of a dynamical system. And throughout this course today, we will call this just the belief. So we are asking the question like, what is the belief about the state of the system at time t, which is equivalent to the probability that the system is in state xt, given all the controls and all the observations that we have seen thus far. And so this is basically what we're interested in. A few more is like independence assumptions that you typically, or for those of you who know about Bayes network, that are pretty common. So this is one that we will see in a few seconds being applied. So what we are asking for, or given we are in a situation where we have a measurement ZT, and we want to know the probability that of ZT given all the states thus far, the system was in thus far, so from 0 to t, all the previous measurements and all the controls. And obviously, if you think about a mobile robot moving around, then consecutive measurements are not necessarily independent. The reason for this is, like if I tell you that I see a green light, and then I move only a little bit, the chances are extremely high that I still see a green light. And so which basically means that measurements are not independent. However, if I tell you in which state I am, then all of a sudden it boils down to just the uncertainty of the particular measurement, which basically means that then in this case, the previous measurement doesn't tell you anything about the current measurement. And this is visualized in these graphs here by, if I know in which state I am, xt, and I have my measurement zt, then wherever I go, I need to go to xt, through xt, which basically means that zt becomes independent of all other nodes, given I have to travel through xt in order to reach the other nodes. Which basically means that we can rewrite this as p of zt given xt. So this is one of the independence assumptions. it's equivalent to this conditional independence assumption that we saw just a few seconds ago on the previous slide. And then we will have another one, which is P of xt given x1 to t minus 1, z1 to t minus 1, and u1 to t. Right, so this is like basically this node over here, and then we are having like all the anti-chain to the left, the x's, and the u's, including that one, and the z's from here on. It turns out that once we have xt minus 1, like again, same argument as before, every node that we have to travel through xt minus 1 gets basically independent of xt and vice versa, so that we can get rid of all of these nodes. And what is remaining then is that P of xt that this is equivalent to P of xt given xt minus 1 and ut. There's an independence assumption that we will do. There's a further independence assumption, which basically says that xt is independent of ut plus 1 given its predecessors, or its anchors does in this case, xt minus 1 and ut. And this is also something, one that we will utilize directly in the derivation. Further assumptions are that the world doesn't change. The noise is independent, so the sensors do not directly physically or the sensor individual measurements are not directly influenced by previous ones, right? And that also the models that we are having are correct and that there are no approximation errors, which is unfortunately not true in all cases, but it's still, despite these assumptions, that what we are going to end up with is going to be pretty robust, as we will see. So now what we are going to do is we are going to basically derive the Bayes filter, right? So what we are interested in is the belief in xt, right, which is the posterior probability of being in xt given all controls and all observations. The first that we are going to do is we are going to apply Bayes' rule here. And in this, we are going to consider like u1 to ut as background knowledge. And when you have a closer look at Bayes' rule, let me go back here quickly. ABC, it's too far away. So then we're going to explain this. So if you have a closer look at this, right, so what Bayes' rule basically does is it basically says that if you only have P of xt given zt, this is going to be P of zt given xt times P of xt divided by P of zt. And what we are going to do now is we're going to treat all of this as background knowledge. And by doing so, we are ending up with this equation over here. So u1 to ut is nothing else but background knowledge. So our prior would be P of zt given xt plus the background knowledge times P of xt given the background knowledge. And then we have here in the front, we do have the normalizer, which would be P of zt given the background knowledge, right? But as it turns out, that doesn't contain xt anymore, so it's a constant for every xt, which is why we denote this just by an eta over here. And if you now have a closer look at this, again, like P of zt given xt, plus everything that happened before, right? So from all these nodes, we basically have to travel through xt in order to get to zt, which basically means that we can remove all of those in order to simplify the equation. So this directly ends up being eta times P of zt given xt times this term over here. Right? And now we are going to have a closer look at this one, right? So this is basically the probability of being in xt given all the controls thus far and all the measurements up to zt minus 1. What we're now doing is we are doing a marginalization trick. We are going to integrate over the potential prior pose xt minus 1. So we replace this term by an integral in which we do basically the marginalization. And this is nothing else but P of xt, then all the values that we see here, and xt minus 1 times P of xt minus 1 given all of this over here, right? dxt minus 1. This is nothing else but this marginalization that we have seen a few slides ago. And again, now we can apply this independence assumptions that we were having, where we are basically saying that this only depends on ut and xt minus 1. These are the two parents that we actually need for this, and all the rest is then being independent once we have those two. And this is the next simplification that we are doing. So we're ending up with like eta times p of zt given xt, the integral p of xt given ut and xt minus 1. And then we have p of xt minus 1, u1, z1, ut minus 1, zt minus 1, and ut. And this looks a little bit awkward here, this ut, because it's like given we are in like xt minus 1 over here, because that seems to be the future action. Fortunately, that's something that we talked about here, right? This ut is independent of xt minus 1, given we know all the parents. Right? And this is something that we can do next in order to simplify this further, so we can basically remove ut from this equation, which basically gives us this term over here. And now we see a nice recursive structure. We do have p of xt given u1 to zt, and here we have p of xt minus 1 given u1 to zt minus 1. And the rest are the two models that we were having before. So this basically ends up being this recursive Bayes filter equation where the belief at time xt is obtained from the belief at time xt minus 1 by integrating over all prior potential positions and summing up summing up basically the probability that we end up in xt, like having been in xt minus 1 before executing action ut, times the probability that we were in xt minus 1 before. And then we multiply the resulting probability with the likelihood of measuring zt given we are in xt. And this eta here, once again, is just the normalization constant that makes sure that val of xt sums up to 1 over all x. And this is basically the algorithm that we are using now for this purpose. It's the so-called recursive Bayes filter. We're basically, whenever we obtain a measurement, like so this is even in a way that it doesn't need to come in the synchronized fashion. Like whenever we obtain a measurement, then we multiply the belief by the likelihood of this measurement in order to obtain this term bel prime. And now we are additionally doing this for x. Now we are doing this normalization trick here. We're summing up the normalization constant by basically using this likelihood of the measurement times the prior, which basically gives us integrated over all x in the end the normalization constant. And once we have this, we divide all the bel primes by eta, which then gives us the belief, the belief that is normalized to 1. And whenever we have an action, then we are basically performing this integral. For every x, we calculate its probability, or the probability that the system is in this state, by integrating over all potential prior states and multiplying that by the probability of ending up in x, given we were in x prime before and executed action u. And once we have done this, we can return this belief. So this is basically the implementation of this Bayes filter. Here's the equation again. So these equations are actually pretty, basis, or this equation is pretty basis for plenty of mathematical concepts. Basically the Kalman filter, the particle filters, hidden Markov models, dynamic Bayesian networks, and also the basis for partially observable Markov decision processes. It's pretty interesting, even like tools like the Kalman filter, which has a completely different mathematical representation, right, is actually a special case of the recursive Bayes filter, simply by like reducing it to Gaussians. And if you make this assumption that your belief, so this term over here, right, is just a Gaussian, this is a Gaussian, and this is a Gaussian, then you basically stay in the Gaussian world, and then this entire equation boils down to exactly the equations that you that you know from the Kalman filter. So what we're going to do now is, or in principle, we're going to look how to use this for probabilistic localization, basically trying to figure out where the vehicle is in its environment. And we're going to do this like here in this example, like assuming that in the beginning we have a uniform prior. This term over here, what we see is basically the sensor model. Right? Let's assume the robot detects that it is in front of a door, right? And this is like proportional to our sensor model here. Our sensor model looks similar like this. Then the resulting belief will be this red curve over here normalized to 1, where basically we have high probability of being in front of a door and low probability of being somewhere else. And when we move, then we execute this integral. Right? We are basically integrating over all potential prior states, which corresponds to that what is typically called a convolution. So we are basically smoothing this belief and at the same time shifting it according to the robot's motion. And so the resulting curve will basically be smoothed and a little bit shifted. And once we observe the door again, then what we do then basically is like we multiply this belief over here that we are having by a sensor model that is proportional to that function and then normalize it again. In the end, that basically means that we are multiplying those two curves over here. And this is exactly what you see in the 5th row. So basically the resulting belief of the system relative about what its current state is and or where it currently is. And what you can see here is that there's 5 peaks. Like one peak is consistent with 2 observations, this one here, like with those 2 observations. And then we have 4 more peaks that are consistent with only 1 observation. So this is basically that's what we would like to obtain from this model. Here again is the equation. And the applications of this are localization, SLAM, object tracking, mapping, and many more. So in order to do so, like to truly implement this, what we want to know is like how can we basically represent this belief of being in XT. And in localization, we typically assume that we are given a map M as a background knowledge. So in principle, we would need to add this in every place. But in order not to mess up the equations, we can also just drop it and assume that throughout the localization process, we will assume that there's a map always given. Right? So that basically also means that our sensor model, P of ZT given XT and M, right, which is the exact specification of this, and typically would also assume this to be true for the motion model. But in practice, it is often abstracted to not include the map. But in fact, the map can provide useful information about potential movements of the system. So, for example, the robot cannot move through walls, and which basically would mean that dropping the map by dropping the map, we lose a lot of information, which is true, but in practice, it is often only used in this approximated form. So how are we going to do this now, right? So what can you expect from the rest of this presentation? What we are going to do is we are going to basically implement this and see how this can be done, right? How can we build a self-driving car that knows where it is? And in order to do this, we basically need to specify how to calculate this. How do we calculate the likelihood of observations? How do we calculate this, right? How do we implement the world model, right? So how can we calculate the likelihood of ending up in XT, given we were in XT minus 1 before and executed action UT? And then we also need to talk about how can we actually represent the belief. We spoke a little bit about this when talking about the Kalman filter, and this would be just the Gaussian. But as we have seen before, the world is not always Gaussian, at least not when it comes to global localization. So in order to like talk about the sensor model, we particularly need to also talk about like what sensors will be used throughout this process. And like when you look at sensors in robotics, there are plenty of those. And what we are going to focus about is like proximity sensors, and in particularly distance sensors. But you can also do this with other cameras, with other sensors as well, for example, cameras and so on and so forth. So and even GPS. So this all can be integrated in this context. So let's look a little bit at proximity sensors. So let's assume you want to do this in a valet parking application, or you do want to have a logistics robot traveling on factory floors. You basically, what you're interested in is using the ultrasound measurements or the LiDAR measurements to perform, to estimate the pose of the vehicle. And problem there is that it's not always as perfect as you see here in the center, but in particular when it comes to dynamic environments where plenty of dynamic objects or humans or other traffic participants around you, then that might end up being like pretty corrupted. So we will have like noisy measurements or erroneous measurements simply because of the dynamics in the environment. So the central task that we are going to look into now is how can we calculate P of Z given X and the map. So the probability of a measurement Z given that the robot is at position X. That is what we actually need for implementing this. And yeah, where do these probabilities come from? That's the key question. And what we are going to do is we are going to try to explain a measurement, right? So how does a measurement get into the channel? How is it generated? Basically, that's what we're asking. And that model that we are going to talk about is a so-called beam-based model, because we are looking for typically these ultrasound beams or a LiDAR beam, and we are trying to figure out what are the potential failure cases and how can we represent them in such a sensor model. As a upfront warning, like all sensor models are just models and just approximations. And this is also not the model that we are going to talk about here is not the perfect model. It is just one model that you might use to start with and implement this on your vehicle. Turns out to be pretty robust already, but there's like plenty of models out there. And there's plenty of opportunities to also do better than that I was described here on these slides. Usually, what you do when you look at measurements from a LiDAR or an ultrasound, you get like something like K measurements. Right? When you have an ultrasound ring on a robot, you have typically something like 24 ultrasounds or so in this order. And then LiDARs typically come within higher resolution. So there's LiDARs with 181 laser beams or even with 361 beams, and even more when you go to 3D LiDARs. So basically, these are individual light rays that are going to be sent out. These are typical time of flight sensors, which basically measure the time it requires until the measurement or the light beam or the reflection from the environment comes back. And in order to not complicate things too much, what typically does is one assumes an independence of the individual beams in the LiDAR, which is in fact an approximation and also a pretty severe approximation. So simply because of in the context of dynamic environments, there's a substantial dependency between neighboring LiDAR beams. And so this is a substantial approximation that actually needs to be carefully looked at when implementing this. But what we are doing here is we are just looking at one individual beam. And so that's what we are doing. We are treating these individual beams independent. Now let's look at typical errors that might happen, right? So here's an ultrasound beam or set of ultrasound beams projected in an environment. Yellow are the individual beams. Black are the obstacles that you see in the environment. Basically a corridor with doorways over here, right? And these doorways are a little bit indented. So what you can see over here is basically, first of all, there's good ones, right? There are these beams that are reflected by the obstacles that we know, by things that we have in the map, which is good, right? So that is what we actually want. The sensor should reflect what we expect or what is out there. Right? That's what a sensor is being made for. But there's also others, right? So there's beams reflected by people, right? So this here is basically two students standing in the room or in the hallway at the very same time, and which are not contained in the map, and producing shorter measurements than expected. And then there's also another one, this one over here, which is an interesting case. You spoke about independency of measurements before. And what happens in the context of ultrasound is that what is called crosstalk, because of the slow time, the slow velocity of sound, one typically has to fire all these sensors in parallel. And then it often happens that the sound emitted from one sensor is reflected by the environment and gets into the neighboring sensor, into the receiver of the neighboring sensor, which basically then means that we get a shorter measurement than expected. And so that's a typical property of these. Yeah, and then you might have even that what is called a random measurement whatsoever. It could be by dynamic objects, but also simple failures. And then also maximum range measurements that are that you find on all like ultrasounds or on all range sensors or time of flight sensors, because usually they emit a signal and wait until the echo comes back. And this is a limited period of time, and whenever this time expires, the time expires that the sensor waits, then this defines the maximum range that you can measure with the sensor, which is something that you typically get with ultrasounds and even LiDARs. So these measurements can basically be caused or reflected by known obstacles, crosstalk, unexpected obstacles, or just miss all obstacles. That is also like what you find in ultrasounds as well as in LiDARs, specular reflections due to very smooth surfaces or glass in the context of LiDAR, or even mirrors. Yeah, and then in fact, the errors that we get is like the normal measuring uncertainty. The position of known obstacles might vary, so even like no map is perfect. The position of additional obstacles not contained in the map, or even that an obstacle is missed entirely. So the key idea of this beam-based model is to basically get away from this location dependency, right? So what you see here is that we need to estimate the probability of the observation given the robot is in state X, which is basically this likelihood of this measurement given robot is in X and the map is M. And what we're doing now is we're basically performing that what is called a raycasting operation, right? So we basically look at the pose X and the map M and ask ourselves, like, which distance would we actually expect? What is the actual distance that we would expect given the robot is in X in the map M? So you're basically like performing a raycasting operation and measuring the distance in the map from the robot location in the direction of this measurement Z. And then what we are then doing is comparing this expected distance to the distance measured. That's what we see over here. So basically, this visualizes that we project the robot into the map, look at what distance would we expect, and then we are going to calculate the likelihood of Z given the expected measurement. And by doing so, you're basically abstracting from the individual location. And there are different types of sensor noise that we now can or that we now need to deal with, right? So let's assume the sensor actually hits the object or the measurement, and we actually measure that object over there. What we then can do is we can represent this by a standard Gaussian distribution, which basically represents the measurement uncertainty. The second is unexpected obstacles. Turns out that this can be nicely represented by an exponential distribution, because there's a very interesting explanation for this, but due to the limited time, it's impossible here right now to explain this. But if you run into me once, then I'll be happy to explain this to you. Right? So it's basically the an exponential distribution that ends there where the expected measurement is, simply because dynamic obstacles behind obstacles that we know don't play a role. Then we have random measurements, crosstalk, etc., that might lead to errors. And here in this case, we just represented by a constant. And then finally, we also represent the maximum range by just the constant at the max range value. And the anti-likelihood function now is nothing else but a linear combination of those four components. So we're basically having like scaling parameters over here, and then mix them up with the scaling or mixture parameters. That's basically that's what we are doing here. Key question is, how do we get these scaling parameters? And this is actually also very interesting how to do this. You can basically use statistics, right? So you basically take your robot into your environment for which you have a map. And let's assume you're already able to perform localization. Then you can basically look into exactly this distribution, right? Let's assume the expected distance to an object is 3 meters. Like, which distances do I actually measure? And this is the plot for sonar in a specific environment. And here is the same for a LiDAR. What you can see is that the LiDAR is way more concentrated around the expected distance, although it's also like sometimes measuring like smaller values, dynamic objects, or just random measurements. It's then when the object is, for example, at an edge, not really hit by the LiDAR beam. And then what you do is you basically fit this function to this data, and then you obtain nice like functions like this over here. The histogram in the background is basically a histogram about these values over here that you see for these exact distances. Yeah, and this is the advantage of this now, is that you can actually, like, if you pre-calculate this, you can do this you can basically store this in a table, which then provides you with just one table lookup, or requires just one table lookup to calculate your likelihoods, which is particularly useful when you have many sensors and many poses where you actually need to evaluate your likelihood. So that's what we looked at right now. So what we see now is like how to actually calculate this value P of Z given xt. Then we are going to look into the second one, right? Now, how can we actually calculate P of xt given ut and xt minus 1? Here we are, like, just to let you know, this is two trajectories. The left-hand side shows the trajectory actually taken by the robot, more or less, as far as we know. And the red one over here, that is what you typically obtain by that what is called wheel encoders. Right? Wheel encoders, let me see, things like this over here, a tiny little discs that basically measure the angle or the rotation of the wheels. And then what you do is you're basically using trigonometry to calculate the trajectory. Right? And this is what you see here. And when you do this, then you can see that you can never actually trust your trigonometry. The odometry, sorry. Okay, what we are going to do now is we're basically trying to implement this function here, P of xt given xt minus 1 and ut. So that's the idea. And for this, we need to look into like how we represent this or mathematically. So mathematically, odometry works in a way that we typically get from this system, right, the current pose of the vehicle, which in x, y, and the orientation theta of the vehicle. That's what we are getting. And if you now look into potential reasons let's skip this quickly. If you look into the odometry of the vehicle, so when the robot moves from one pose to the next, then this can typically be represented by a transformation that consists of an initial rotation. So in order to get from the left-hand side to the right-hand side point, the robot first has to rotate, then it has to translate, and then it has to rotate again. And every movement that the robot does can be represented by those three values, or three such values, right? So initial rotation, final rotation, and a translation. And this is what we are now looking into. So what we are basically getting from the odometry is like a stream of poses, and what we are doing is we are converting this into those three values here, and from that we are going to calculate these likelihoods. Right? So in order to, like, if you have two such poses, then you can basically calculate this using these functions over here. Yeah, just to implementation detail. And then we are also looking into potential noises there, right? So when we just look into these elementary actions, initial rotation, translation, final rotation, right, then they are typically affected by noise that we add to those values in order to get actually distributions from which we then can calculate likelihoods of, for example, like rotation, translation, and second rotation, which with a head independent, which basically means that what is the likelihood of this particular movement once we recorded this movement or we got this movement from the odometry. And this is the key idea of this approach. Like just in order to calculate this in an efficient way, you can either use Gaussians here, but you can also use triangular distributions, or so we actually use this as well, just for efficiency reasons and to speed up processes. Right, so what we are going to do is then we are going to have a function that gives us like the probability for a query point and a given standard deviation around 0 in this case, but you could also generalize this to another point, but that is just shifting the Gaussian along the x-axis. And the same for the triangular distribution. But now, like if you think about this, like calculating the posterior given x prime, and the odometry. So we are having two query points here. So this is what we call the hypothesis, and this is what the odometry tells us. And now we're doing exactly that, what I mentioned before. So we're basically saying, what if the robot moved from x to x prime? Given the robot, the odometry tells us the robot moved from x bar to x bar prime. What we're doing here is we're basically doing nothing else but calculating the odometry parameters and the query parameters, or the delta, these three deltas for the query values. And then we are basically evaluating the probability of these query values given the odometry parameters. This is what we see here, and shifted to 0 by this difference. So this is basically what we're doing, and in the end, we're just returning the product of this. This is already sufficient to get decent distributions out of this. So here's, for example, this plotted for like a certain translational movement, and this ends up. And typically in these, like if you accumulate this over time, like in these banana-shaped distributions, and depending on how your movements are, then the uncertainty is different. And so this is how we basically calculate these likelihoods, and black means high likelihood and gray means lower likelihood. But there's also another way of dealing with this, and this is something that we are going to use in the implementation, like for the so-called like sampling-based representations. We're basically trying to figure out how to represent a function by a set of particles or samples. And this is like what you can always do, like you can always approximate an arbitrary function by a set of hypotheses, and then the height of this function is then proportional to the density of these particles. So this is the key idea of this representation. So low values mean few particles, high values means high density of particles. And the idea now is like that we, instead of evaluating these likelihoods, what we are going to do is we're going to sample from the so-called motion model. So we're going to implement a function that allows us to guess a potential new pose of the robot, given the robot was in X before and executed the odometry command. And so you can, for example, sample from a normal distribution by just using this function over here. Is relatively efficient. Right, and here's just one example with 1 million samples sampled from this function. It actually looks relatively nicely like a Gaussian here. Right? But there's also like ways to sample from a triangular distribution. Right? You basically perform this function over here, which is also pretty efficient. Right, so here's examples for the triangular distribution, just to you know. But you can also sample from arbitrary functions. Right? So if I give you an arbitrary function, then there's a specific and interesting method that allows you to sample from this arbitrary function. It is so-called rejection sampling. So let's assume we have this blue function over here. Right? So what we are interested in is like getting samples that are distributed according to the height of this function. All that we need to know is like this interval from where to where and the maximum height or any threshold that is beyond or above the maximum of f. Right? And what we are doing now is we are guessing an x, we are guessing a y, and if f of x is larger than y, then we keep x, otherwise we reject it. Right? So here's like one thing, we guess an x, we guess a y, which is in this case larger than f of x, we reject y in this case. In another case where we have f of x over here and we sample over there, then we would keep y prime in this case. Right? So this is the key idea of this approach. It's called rejection sampling. It's a way to sample basically from arbitrary distributions. So this is the implementation of this. Yes, right. There are cases in which, for example, when this function is Dirac, has just one single peak or even many peaks that have width 0, then this function will never terminate. Right? So this is something that you need to be very concerned about when you use this algorithm. And then you can also do the very same as we did before, but now instead of evaluating this motion model, we can actually directly sample from it. Right? So we take this odometry measurement that we are having, or the actions, initial rotation, final rotation, translation, plus the current pose, and then we sample new deltas from sampling from a Gaussian over here, for example, and adding this to the individual parameters, and from this we calculate the new resulting poses or the position plus orientation. Right? And when you do this, then you obtain in this way like a sample-based representation of your belief. And so this is what you can obtain with this representation. Right? And here's another way how this evolves over time. And again, you see this beautiful banana-shaped structure over here, which you typically obtain by applying this motion model. So we are right now over here, right? So we know how to calculate this. What is now missing is like, how can we represent this? And as I mentioned, there are different ways for doing this. And the one implementation that I want to show you today is basically the so-called particle filter, which basically represents this function by a set of hypotheses. But there's other ways as well. As I said, Gaussians, you can also go to discrete approximation. So all of this is possible. The particle filter is like a way to efficiently represent non-Gaussian distributions. It basically uses a set of hypotheses, we call those particles, in order to represent this function. And then the key idea of this is a so-called survival of the fittest scheme, to basically maintain those hypotheses that fit or have the most contribution to the representation. So in principle, this is a set, actually a multi-set for the mathematicians among you, of weighted samples. Right? So we have a state hypothesis. In the simple case, a robot lives on a plane. This is x, y, and its orientation. And we do have an importance weight. right? And so that's what we are having. And basically, by doing so, this importance weight is basically also used in like as a weight over here in order to like represent the importance of every individual sample. That's what we are going to use throughout this algorithm. So this is like just a direct function over here. That is one if x equals the state of the hypothesis and 0 otherwise. It's basically what we're having here is now kind of like if all the importance weights are identical, then we have just like a height of wi there, and otherwise it's going to be 1. As I mentioned, right, they can be used to represent functions, but in our case, we also allow them to not only have the identical height, but also have different heights. And we will also briefly describe how this is going to be resolved. So how does this particle filter now work? So what we are basically doing is like, we are having a set of hypotheses, and every hypothesis represents a potential state. And let's start with x prime. So the first step that we're doing is basically we are passing this to the motion model, and we have seen how we can sample according to the motion model. Right? We are given a current hypothesis, x prime, and we are given the control. And what we are now doing is we are guessing a potential outcome of the action u and x prime by sampling from this motion model. Right? And we are getting a potential new pose for this hypothesis. Next step is we calculate the importance weight of each particle, and in localization, it has a nice property that this is exactly to the observation likelihood, given the state of the particle. Right? So it's basically the likelihood of that observation given the state of the particle. Then we have weighted particles. And then the next step is that we resample. And steps 1 and 3 are often done jointly, because after resampling, you can directly take this new one and pass it through the motion model. Right? So that's then you don't need to run twice over this. And here we go. Here's the algorithm. Right? It's basically the first step is sample from the motion model. Right? Then compute the importance weight. We also need to normalize these particles, so that's why we are updating the normalization factor, and then in the very end we normalize the weight that we basically have the sum of 1 for all the particle weights, right? And then this here basically is the resampling operation, where we basically replicate the particles proportional to their importance weights. That's something that we are going to talk in a second. So what does resampling do, right? So usually what we are having now is we are having particles plus or weighted particles. And what we are interested in is we want to have like a new particle set where all the weights are identical. So what we are doing is we are basically drawing from this set of particles, and in a way that it is like we're drawing a particle from the set of particles in a way that this is proportional to the importance weight, which basically means, this brings us back to the survival of the fittest, that higher important particles with higher importance weights will have a higher chance of being replicated. Particles with low importance weights will have a low chance of being replicated. And typically this is done n times with replacement to get a new sample set S prime. So that's what we are doing. And mathematically, this is done usually with this type of roulette wheel concept, or this is a kind of like a representation of that, what is happening there. So let's assume we are having a roulette wheel where the individual holes are exactly the size of the importance weights. And what we are doing now is we are guessing an initial angle in this roulette wheel, and then we are proceeding in this roulette wheel with a step size of 1 divided by n times 2 pi. And then we're basically picking all particles in which this particular angle then falls. And from this process, we get n new particles. And we also have like then them drawn in a way that they that they are replicated proportional to their importance weights in normal cases on average. So this is basically that what we are doing here. This is called stochastic universal sampling or systematic resampling. There's a relatively good complexity. We only need to touch every particle once and is easy to implement and has also low variance. So when you repeat this over and over, then the number of selected particles are not too diverse. So this is a procedure for this. I don't have time to go through this, but it's a pretty interesting algorithm. If you should have time, my recommendation is to actually run this once on paper to understand how this actually works. It's actually pretty cool how this is implemented. And for the experts, the question is like, why do we need here this half-open interval? Right? So if you really want to dive into it and run this algorithm and answer that question. And here's this thing in action, right? So this is what you can see, like when you implement such a particle filter. This has been based on ultrasounds over here in the very beginning. Like there were 10,000 hypotheses. The robot actually traveled along this corridor over here and into this room. I will run this again in a second. What you can see is that these particles through this resampling operation actually focus on the true pose of the vehicle and basically allow the robot to relatively accurately track its pose. This environment is particularly difficult for localization because this corridor here is rotationally symmetric, and then also the doorways look the same to the robot, mostly given these uncertain ultrasound sensors. And so let me go there again. So in the very beginning, you see that these hypotheses focus more or less in the corridor. Then you have different peaks relatively same distance to the door, right? And then at some point in time, the robot figures out where it is relative to the end of the corridor. It doesn't know as to whether it's moving left or right. And this can only be resolved by moving into these rooms because those two rooms look different. The robot will only know once it is over here as to whether it's actually here or down there. So this is what these systems can do. There's a property that is hard to realize with other representations like with Kalman filters, because Kalman filters, this Gaussian representation doesn't really allow you to have like multimodal beliefs in which you have a high uncertainty about where you actually are. Right? And with this, we also implemented, for example, a car localization was a valet parking application that we once implemented in Stanford with the Stanford parking garage with Stanley, the robot, navigating through this parking garage. And what we used here is this 3D representation of the parking garage to actually estimate the position of the vehicle in the garage. It's the very same approach for this. And you might ask now the question, how accurate does this actually get? Right? And here is something that we showed a few years ago when we actually used this KUKA 11-ton KUKA OmniMove system to in typical factory floors. It was an application where we were supposed to transport 777 fuselages through the construction sites in Seattle in the US. And this was just a test vehicle to estimate like how accurate the localization can get. And this is a test where we actually used a mocap system to estimate the pose of the vehicle. And it's actually not the absolute pose, but the repetition pose. So when mocap systems are super accurate when it comes to the question of is the vehicle at the very same pose again. And this is what we tried here. This system is doing this repetitive movements, and we are also adding these wooden boxes over here simply because these LiDARs that are mounted at a height of 10 centimeters are then reflected by these so-called dynamic objects that you see around. And then what you can see is that the localization accuracy is below 2 millimeters in this case. Even when it comes to the dynamic environment, so we put a lot of like dynamic stuff there, then it doesn't really get worse. Right? And this is something that what you can really achieve with this technology. Right? And it also shows that you can actually like very accurately localize vehicles on shop floors, but same is for self-driving cars. In practice, we see these we see that these cars can localize themselves with up to a millimeter accuracy, even in outdoor environments. So this is only localization, but you can do the same thing with mapping. So if you want to do like build a map and at the same time figure out where you are, the very famous SLAM problem, simultaneous localization and mapping, right, where you're not given a map in the very beginning, so the robot has to do basically both at the same time, figure out what the world looks like, and then at the same time figure out where it is. Can do the very same thing with this like so-called RAW black-localized particle filter. This is how it is called in this case. You are basically having the individual hypotheses, not only about the pose of the vehicle, but about the pose of the vehicle and the map. And so which basically means that every hypothesis represents a potential map plus the pose of the vehicle in that map. Right? And so basically that every like particle has its own map and that it carries around with, and then everything stays the same. And you can actually do this also then in practical environments or in real-world applications. This is an example here where you can see the former Intel lab being mapped with a robot, and what the system here does, it basically is recovering the pose of the vehicle in this environment, and from that then you can render the underlying map. And so this is something that has been also being very, very efficient, and the advantage of this approach is that it actually also works in an online fashion, that you can run it while the robot is moving, and you do not need to record all the data and then construct the map retrospectively. But still, the very same is like these post-graph systems that basically do not estimate the posterior, but rather maximize it. Right? So this is basically maximizing a likelihood is minimizing an error. And so this is why this leads to like quadratic optimization problems that are then being solved. And this is the current state of the art still when it comes to probabilistic approaches to mapping or simultaneous localization and mapping. And with this, you can actually generate highly accurate maps. For example, like here, this is a startup that I'm having. This is a reconstruction that we did more than 2 years ago. It's a leaning tower in Pisa, and it's basically the most accurate model of this system. We have, in order to create these models, we are flying with a 3D scanner over these buildings, and then we can also take these scanners into the buildings, which will allow us then to get an indoor and outdoor model, an accurate one. Here is the cathedral in Freiburg, the most accurate indoor-outdoor model of the Freiburg Cathedral, where you can basically see also like the crypta down here and the cellar underneath the church. And they're using this, for example, identifying changes or things that fell off the building, things like that. This is pretty important for these type of cultural preservation endeavors. The key question now is like how we all know that there has been this deep learning revolution, and at the end I want to briefly talk about this, like how you can actually combine this with maybe more modern approaches like deep learning. And here's one example. You can see semantic segmentation, a typical task that you encounter or find when it comes to developing a self-driving car. And the interesting aspect here is when you look at the very same graph that I showed before with the individual components of a self-driving car stack, then we see that like the deep learning based approaches are particularly good when it comes to this interpretation part, namely this question like, what does the sensor actually tell me? Whereas these probabilistic ones are probably a little bit stronger when it comes to mapping and localization, what we have seen before. And the key question, like when you see something like this, is always like, is there a way to properly combine them? And the problem is that, like when you look at the deep learning-based space, that we often like only get like the maximum likelihood out of it, and not rather like a real distribution. We don't get likelihoods, which is a problem because, like in localization, we actually need proper and calibrated likelihoods. And this is a key problem when it comes to developing self-driving cars, and namely that these components over here typically need to provide you with proper calibrated likelihoods in order to perform localization tasks and even other things like prediction and so on. They typically rely on accurate probabilities. One way of doing this is like in augmenting these tasks with proper calibrated probabilities is something that I have been working on over the past years with one of my students who's graduating right now. Like this question of how can we actually perform semantic segmentation and provide proper uncertainties at the very same time. So here you can, for example, see like the outcome for the semantic segmentation task. And what is nice over here is that you basically at the borders between different classes, you see a high uncertainty. High uncertainty means bright, low uncertainty means dark. And so at the edges of these classes, you see typically high uncertainty. And the same over for the instance segmentation task. Right? Here you also see at the borders of the individual instances, you see high uncertainties, which is exactly that what you would expect from such a system. And when you combine those two, you get that what is called panoptic uncertainties, and which is basically the combination of semantic and instance uncertainties. And that's something that we implemented in a localization system. So we are basically in a particle filter, right? In order to basically, again, if a particle filter is able to work with these uncertainties, then that basically means that there must be calibrated, right? So there must be meaningful uncertainties that can be used properly in the downstream task of a self-driving car stack. And on the right-hand side, you can basically see a particle filter working using these individual classes that you see here, like panoptic uncertainties, road boundaries, street signs, poles, and so on. Here now the car is like stuck in front of a traffic light. And whenever the particle cloud expands, then you see that result means that there's a higher uncertainty. Red is ground truth and blue is predicted. Ground truth is obtained here using a differential GPS. And whenever the particles stretch out in the direction of travel, then the reason for this is that there are too few point features that the robot could actually, or the car could use to actually exactly figure out where it is in its environment. And that also then sometimes leads to estimation errors. Yeah, so this is basically a challenge that I think is an area where still there is like is some demand, like how to properly combine these two approaches to basically get the best out of both worlds, to have the robustness of state estimation processes and the performance of these semantic interpretation tasks, and combine them in a proper fashion. And then the last question that I want to briefly cover is this question of like, what about foundation models? So we all see right now like a revolution of things or revolution of developments, or revolutionary developments. Let me put it that way. In all kinds of contexts, it's not only perception but also like interpretation, manipulation, and so on and so forth. Yeah, this is an interesting question. So we also recently worked on this paper here, visual language maps for robot navigation, basically goes beyond that what has been done in probabilistic robotics and typical software stacks. like with these nowadays foundation models, and that's what is happening here is we are basically, there's still a 3D model behind this, and we are in this case mapping the embeddings found in or provided by the foundation model onto these voxels in order to perform then tasks like move to the right of the chair, which has always been difficult, in which these purely geometry-based approaches that I presented earlier are not capable of doing. Right? So we all know how difficult it has been for years to perform tasks like move to the plant or so on. Right? I used to say this, every of these tasks here is one PhD student life, excuse me, simply because you would have to write an individual classifier for every of these tasks. And this is now like given for free. So the advantage now is that we can basically use these tools for navigation tasks that have previously not been possible. But still, like even in this work, we are still relying on this underlying 3D voxel grid. And my key question, and that what I would like to understand in the future is like, can we somehow get rid of these 3D representations? And this is something that you also see right now. There's plenty of tasks of approaches who can perform navigation without an underlying 3D structure. So for me, this is the most relevant research question. Like, can we actually have a robot navigation system that doesn't rely on these accurate maps anymore, which basically also would mean that we probably don't need SLAM anymore and that we don't need localization anymore. This is an interesting question. And with that, I would actually like to conclude here. And I hope that I could show you that probabilistic approaches has quite some power, or have quite some power for robust navigation, that integrating them with deep learning-based perception approaches is a challenge, but it's a way to go when you basically think about like building a robust system. The key question now is like, can we maybe even build a robotics foundation model that does the same thing at the very same time? I do not know whether I will experience this in my life, but I'm pretty convinced that you young folks will make tremendous progress in that direction. And with that, I want to stop and thank you for coming.
Yeah. So thank you very much for the talk. Now we have some time for questions, and I think IIT needs to leave earlier. So maybe if IIT has some questions, they can start.
Yes, one best. It seems that from our side there are no questions. Okay, but really interesting presentation. Thank you very much.
Any questions from here? I have a question about the last part that you're mentioning, that whether these models are, if it can be. I mean, the question of can be, yes, there could be an alternative where you don't need the map, but I guess the question is more like how useful or how the methods compare, no? How do you see this, that there will be really a trend on getting rid of these 3D models, or they will still be needed because it's more useful having a 3D interpretable model than not having it?
Yeah, that's a very good question. I mean, normally it is, my opinion is that these maps or these models are super helpful in taking or in building a system, right? And developing a robust robot, factory floors or wherever. However, right, these models are also causing problems. Like, for example, they are one of the reasons why there is no level 5 car out in the world right now. Like we have level 4 cars. Right? So the level 4 cars heavily rely on maps. Right? So there is some sort of pressure, I would say, to basically look into this question of can we navigate without a map? That would be definitely a substantial step forward. Yeah, but so I know, like, I gave this presentation to basically show you how to implement like a super robust vehicle these days, but from a research perspective, or from basic research perspective, I would say, hey, let's look into this as well, into this question of can we build a robot that doesn't need a map anymore? And we are pretty far away from this right now, right? So, for example, we cannot do reinforcement learning on top of these foundation models or VLAs and